Thank you everyone for being here. My name is Sina. I'm a PhD candidate at Portland State University. My presentation is early detection of ASR in laboratory concrete prism using ultrasonic Coda wave monitoring. I would like to acknowledge and thank the co-authors and my PhD advisor, Thomas Schumacher, and all the other co-authors, Dr. Tripolra, Dr. Eideker, and Dr. Hafiz. First, let's start with a little bit background. So ASR happens in the concrete because of four main reasons. So the alkalis in the pore solution of the concrete, the alkali hydroxides, they interact with the reactive silica of the aggregates. And in the presence of the calcium and moisture, they can form an ASR gel. This ASR gel, in the presence of the moisture, can propagate and put some tensile force on the concrete and eventually cause cracking. And this is one of the most major concrete durability problems. And also there is a figure here at the bottom right. You can see the reactive aggregates, and this shows the interface of the paste and the aggregate, and this alkalis in the pore solution are interacting with the reactive aggregate, and they are making this product, which is cracking the aggregate and the paste both. And then here are a bit background about the term Coda. So the term Coda was first used by Aki in 1956 in seismology papers. It used to describe multiple scattering in the earth. And this is a very popular term in seismology. So Schneider in 2002 for the first time used the Coda wave interferometry. And later in 2006, he developed the general theory of Coda wave interferometry, which says the total wave field is the superposition of the waves that propagate along all possible scattering paths. So in terms of our work, one of the most interesting works is the Shore's work, if I pronounce correctly, my apologies. So in his master's thesis, he used Coda wave interferometry to distinguish different type of damages in the concrete. And one of the things he looked into was ASR damage. Very interesting work. But one of the limitations of the work was they had to detach the sensors during the experiment. And also the current standards like ASTM standard to monitor the ASR expansion, one of the big limitations is the long duration of the test. It takes for 1 year or 2 years for different goals. And also the other limitation is the manual measurement that we should do at a specific interval. So the operator should have the specimens out and measure their length at different times. So the motivation and objective of our work was to see if we can develop a method that can detect ASR a bit earlier, and also if we can automate the process so we remove the need for manual interruptions by the user, and to collect some measurements that have some physical meaning. So for our experimental setup, I'll start with the mix. So we came up with 3 different mixes. So every constituent in these mixes are the same except the lithium nitrate. So we have 3% of lithium nitrate, 0%, 15%, and 100%. The lithium nitrate mitigates the ASR process, so the 100% is fully mitigated. And then for the cement, we have high alkali cement for all of them. And for the aggregates, we have very highly reactive fine aggregates and non-reactive coarse aggregate. Also, you see an image here. It's part of the experimental setup that I'll go back to this later. So we have 2 locations. It was a collaboration between Portland State University and Oregon State University. In the first location, Oregon State University, our team did the expansion monitoring based on ASTM standard. So they are 3 concrete prisms per mixture, and we had 3 different mix, so 9 total. And also there were a couple of specimens to measure comprehensive strength. And based on these standards, hot measurements taken at regular intervals. Hot measurements means before letting the specimen cool down. So we took them out and measured the length and put them back. At the second location at Portland State University, we had the same mixes, 2 per mix, 2 samples per mix, and we had this ultrasonic monitoring setup. So this setup was prepared by more than a year of experimentation. We came up with the setup which was reliable and robust. So in terms of the coupling, which I see the most important thing, because these kind of experiments and the humidity and the temperature, it causes a lot of interference, and the coupling is very important. So my advisor came up with this beautiful coupling you see here. So it's very robust, and you don't have to worry about the sensors detaching, and you just put the specimens in this cooler you see here, down left here, and the process is automated. I mean, no more interruption. You just run a run button here and let it go for 2-3 months or whatever monitoring period you desire. And the setup is very regular. You see the waveform generator. And as I said, this environmental chamber, it is controlled by a heater to make sure the temperature is constant, 38. And we have 2 different data acquisition systems. One is connected to this PC here, the other to the laptop. And we had 2 samples per mix, and each sample is connected to one of these devices. This itself increases the repeatability of the process. And we use 100 kilohertz of the wave frequency. And again, for experimental setup, we have an image here. So this shows the containers we used at OSU and at PSU, 2 different locations. So at Oregon State, there was this big environmental chamber, and we had these buckets, and we put 2 prisms inside it. And it was always at constant 38-degree temperature. And in our location, we had that cooler. So we used the water heater to make sure that the temperature is always at 38. And we had the transducers attached in this setup underneath the specimen. Okay, in terms of data analysis, so the main idea of the CODA is when multiple scattering happens inside one medium, it can tell us some information about the medium in the wave travels. So we have a transducer here and we have a receiver here. So at the first arrival, which includes the P wave, always is the fastest, it goes directly from transducer to the receiver. But when there are microcracks or other things in the medium, the later portions of the signal, like these portions here, it takes longer for them to arrive. And due to multiple scattering, if we have changes in the, and if we do continuous measurement and we have changes in the medium, these multiple scattering tell us something about this complex path it may take. This is just one example. And yeah, so here at the left, we see the first arrival, including the P wave, and we are taking measurements for 3 months. If we zoom in this section, we see the first arrival. It's not changing or shifting that much from like day 2 to day 84. And then it's at last 3 microseconds, which is equal to 6 samples. But the CODA portion, on the other hand, you can see like there is like more than 60 microsecond in this case. So it's more sensitive. The later portions of the signal, or the CODA portion, is more sensitive to the changes in the medium. And here's another interesting plot. So this is for mix 3, which is the one fully mitigated, which we don't expect to see ASR happening in it. So we see the x-axis here is the time of measurement. And we see there is not the red plot here, the red graph. It's the first arrival. It's you see there is not that much change from day 0 to day 90. It's not that much sensitive. As we go to the tail of the signal, as we go deeper, like going from 183 microseconds down to the end of the signal, we see this time shift of the coda is getting more and more. So it means like the later portions of the signal are more sensitive, and the hypothesis here is that the coda wave feature is more sensitive to small internal changes such as ASR progression, because this is a controlled environment and everything is the same. So the only variable here is the lithium nitrate of the mixes. So we expect to explain these changes in coda shift to be the reason for that to be the ASR. And here a slide I have all the results in one graph. So I'll start with the bottom one. The x-axis here is the time of measurements, again from day 0 to day 90. And the y-axis in the first plot, the bottom plot, is the expansion. So this is a regular plot of expansion due to ASTM standard. So as we expected, the fully mitigated 100% lithium, there's no expansion happening inside it. But the other two, the one with 15% lithium and the one without lithium, we see the expansion is happening and it crosses the threshold at day 32 and the other one at day 44. And then I go to the top plot, which is our coda wave results. So we tracked one of the traces. Like if I go back to the previous slide, there are different features that we can pick arbitrarily from the tail of the signal. And we go deeper, it shows more. So we picked one around 1300 microseconds, and we tracked it based on the x-axis. So you see the 100% fully mitigated one, it is following this trend, the green one. So there are some interesting things here. First of all, the results for the two Prisms are almost the same, even though they were connected to different devices, but they were the same mix, and we can see the same results for both of them. And we can see distinguishable patterns between the three mixes. And for the 100% lithium, where we expect that there is no ASR, this is like a standard equation. It's like only hydration is happening and concrete is gaining stiffness, and we can derive an equation out of this. But for the other ones, there is a competing mechanism, which is the ASR and progression of the cracks. And we see at first it's going like this, and then it starts to fall down, and the shifts are going negative at some point. It means the signal, instead of coming to the left, it's going to the right, and the shifts are changing. So in order to quantify this in some way, we calculated the slope and the derivative of these plots. And we can see, for example, the red one, it's crossing the zero slope at day 17. If this is a way of quantification, it shows like the changes. It's happening at day 17, and the other one at day 32. Even visually speaking, without any quantification, we can see different trends for these three different mixes very early on. I mean, I can tell the difference like between these mixes and this mix, even at early couple days. Yeah, so to summarize here, the coda shift shows difference earlier than expansion measurements, and the trends are consistent between the different samples. Yeah, and to summarize and conclude my presentation, I can tell the method we came up with more than a year of experimentation is automatic. Automatic means there is no need for manual measurements taken by a lab technician. So you put the prism and attach the sensors inside the cooler, and then you let it be for 3 months. And there is low data variability compared to manual expansion measurement. So what this means is, for expansion measurements, we had 3 mixes 3 prisms per mix, and one data point was always off. So the variance between the same samples was higher comparing to the ultrasonic setup because the trends were similar. And we can say the results were repeatable. I mean, at least for the 2 samples we had for mix, for each mix, we got the same results. And also the earlier detection of ASR. So for the future, we're gonna do petrographic analysis and see if we can verify the results with petrographic analysis. And of course, we need more data to come up with, to validate our hypothesis. And also, we can develop some mathematical or statistical methods that can predict ASR level based on the shift we measure in the coda. It is predictable. Thank you so much for your time. Any questions?
Thank you, Sina, for the presentation. There's a question, says, how difficult was it to be confident that different coda features of interest were properly picked out at different times of curing?
We wrote a small algorithm in MATLAB to do that. So it's we pick a time window. We start at the beginning. We pick a narrow time window that the index of the maximum amplitude inside that window is tracked by that algorithm, and the window is adjusted through all the measurements. So in some cases, because this feature is arbitrarily, it is a bit hard to track it because sometimes it loses amplitude and it gets lost. But there are a lot of these arbitrary features that we can choose, like anywhere in the tail of the signal, as long as it's detectable by the algorithm, it can track it all the time. So yeah, it's a bit tricky, but it's doable.
All right. We still have time for more questions. Please type in if you have any. I was just going to ask one question here is that, so I assume you have done your test on one type of concrete. So do you think if there are other type of concrete, same level of accuracy can be obtained? For example, if you are dealing with SCC, ECC, lightweight concrete, or, well, I think you have done normal weight concrete. So do you think this level of accuracy, the same level of accuracy could be obtained using this method?
Yeah, I can't really tell now if how much is generalizable to like other types of concrete. We need more data on this, but physically it should be possible because any difference between the mixes or in terms of ASR reactivity should somehow be encoded in the signal we record in a very controlled environment. I mean, the information is there. It's all we should do is extract the appropriate feature and do appropriate analysis. So in my opinion, yes, it can be generalizable because it's based on the physics of the waves and materials.
Very good.
Thank you so much for this.
No problem. All right. Thank you, Sina, for the presentation.